Hi, I'm Zor. Welcome to Unizor Education. Today's lecture is about principles of Lagrangian mechanics. Principles in a way that I would like you to understand why we can use Lagrangian mechanics in many cases instead of Newtonian mechanics. And not only why, but also why it's actually logically valid to do this. Basically, my purpose today is to start with Newtonian mechanics and move to Lagrangian in generalized coordinates based on certain objective properties of trajectories which mechanical systems take. Let me make an analogy. If you have, for example, the source of light, and then there is a boundary, let's say this is air and this is glass, let's say. Now, if you have the ray of light going this way, it actually changes the direction and it comes to this point. From here to here, light goes precisely by some trajectory, not this one, not this one, not a straight line. It goes really this way. And why? Because there is a certain principle. In this particular case, the light goes to minimize the time because the speed is different, and what's important is to find trajectory which gives you the smallest amount of time, the least amount of time. So it's objective characteristics of the light, of the trajectory of light. Same thing in mechanics. Mechanical system goes along certain trajectory which is supposed to have certain quality, like minimization of time over there. There is a minimization of so-called action function. It's objective criteria based on which trajectory is chosen. But I would like actually to go there logically, starting from Newtonian mechanics in Cartesian coordinates. And here is where we would like to actually have a very distinct approach. On one hand, we have a mechanical system which actually has certain purely physical properties. It exists in this space. Components of this mechanical system are moving somewhere in some directions based on certain forces, let's say, and we have the second Newton's law, right? And where did we get it? Well, in classical mechanics, this is basically an axiom. So Newtonian second law is an axiom. We based it on certain observation, obviously. It corresponds to our practice, but there is nothing we can derive it from, basically. I mean, we in the old-fashioned classical mechanics, this is the law, and it's like an axiom, basically. Now, from here, I would like to gradually move to Lagrangian logically, and basically to prove that Lagrangian approach is actually not only equivalent to Newtonian in Cartesian system of coordinates, but also it's much better because it's valid in any generalized system of coordinates. So that's my purpose. Okay. So the first we have decided, we have separated physical entity which basically exists in this space and moving along certain trajectories, and let's call it a physical trajectories, and we should actually distinguish it from our view on this particular space and trajectory. Our view is based on certain coordinate system which we have introduced into the space. Let's say it's a coordinate system which is Cartesian, for example, in which case the point point of every object is 3 coordinates. We traditionally call it x, y, and z. And if you have a system, mechanical system of n components, that's basically xi, yi, and zi, for I is from 1 to n. So it's 3n coordinates, 3n numbers. Now all of them are functions of time, right? So 3n functions basically define the trajectory of the system. We have all these 3n functions of time define how every particular component of our mechanical system is moving in space. Okay, so this is a mathematical description of trajectory. So trajectory exists by itself as a physical entity which is completely independent of our view or our instruments, how we view, or measurements, or our coordinate system which we introduced in the space. So it's a system by itself, it works, it moves, it has physical trajectory, independent of our will. And at the same time, we have mathematical trajectory, which is the description of this. And we should really separate these two things. And what's very important in this particular case is to understand that if we will introduce a different coordinate system, it will be different set of functions, obviously, which describe the same physical trajectory. So the same physical trajectory can be described by many different mathematical representation based on our system of coordinates, units of measurements, etc. For example, if you have for instance, two-dimensional space, and you have a circular trajectory, that's basically by itself a physical trajectory which exists outside of our will. But now, if we will introduce a Cartesian system coordinates in the same plane, which has the center as the 0 point, as the origin of coordinates, then we have basically x and y coordinates, and we could say that basically x is equal to r cosine of omega t, and y is equal to r sine omega t. These are two equations. Basically, this is a mathematical description of the trajectory of some object rotating, uniformly rotating with angular speed omega and radius r. At the same time, if you will introduce polar coordinates with base axis corresponding to the same, let's say x, and this is an angle, so you have r, which is radius, and you have theta, which is angle, right? Now, in this particular coordinate system, r of t is equal to r constant, and theta of t is equal to omega t. These are also mathematical description of the same trajectory. I mean, they are completely different. I mean, one set of functions and completely different set of functions, because it's completely different set of coordinates, but they describe the same physical trajectory. So what's important to take from this particular point is that physical reality is one and the same, and it can be described by mathematical tools differently depending on coordinate system, unit of measurements, etc., etc. So that's my first point. Physical reality as a separate entity from our mathematical description of this physical reality. Okay, that's one thing. Now, what's the problem with f is equal to m times a? well, let's do it a little bit more precisely. More precisely, if you have a system of n components, then first of all we have to add I here. So it's not one equation, it's n different equations. And not only that, each one of them is a vector, which means that we actually have 3n equations. We have f(I)x equals to m(I)a(I)x, f(I)y is equal to m(I)a(I)y, and f(I)z is equal to m(I)a(I)z. So we have 3n equations where I is from 1 to n. And what's very important is that these are vectors and these are coordinates. Our Newtonian second law is expressed in very coordinate dependent way. Not only coordinate dependent way, actually it's Cartesian coordinate dependent. Maybe you can do it somehow differently in some other system of coordinates, but basically this is it. I mean, Newtonian second law is very much involved in Cartesian system. It's kind of difficult to do it differently, which sometimes is not convenient. For example, if you're talking about, let's say, a pendulum, what's very important is the only unit of measurement probably and coordinate system would be an angle, because this is constant. So angle is moving. So the whole movement would actually be a function of one coordinate. Angle, not Cartesian coordinate. Angle is not a Cartesian coordinate. Yeah, you can obviously introduce x and y system here, x and y, and put equation based on x and y, but then you have to really add the constraint that x squared plus y squared is equal to r squared, right? Because r is constant. So it's two differential equations for x and y and one constraint, instead of maybe one equation based on angle theta. Obviously, with one coordinate, which is an angle, is much easier, seems to be at least. But we don't have Newton's law based on angles as the only coordinate in this particular case. So it's kind of difficult. So we are tied up in Newtonian system to Cartesian coordinates. Now, I would like actually to do something to move from the concrete Cartesian or any other coordinate system into the general coordinate system, which means it's basically the same equation will be the same in any system. And these equations are Euler-Lagrange equations. You have been introduced to these equations before, but now I would like actually to move towards the concept of action functional and some physical property of trajectory, which gives us the way to universally represent a movement of mechanical system in some equation way, well, Euler-Lagrange equation way, which is independent of coordinates, while Newtonian second law does depend. That's what's very important. Okay. Now, what's our next thing is? All right, so let's so far start with Cartesian system of coordinates. And we know that these equations are basically axioms. Now, just to make my life a little easier, in the previous lecture, which is called Lagrangian mass, I have introduced uniform Cartesian coordinates. I just replace xi, x1, i1, z1, etc., xn, yn, zn with s1, s2, s3, s3n minus 2, s3n minus 1, and s3n. So that's kind of easier, and if I put lowercase n is equal to 3n, instead of these three equations, I can put just one equation, which is y s, well, that's I, is equal to mi ai, not ai, si, coordinate. Double apostrophe means second derivative. Acceleration is second derivative of this, where I belongs from 1 to lowercase n. So these three I have basically replaced to this. Doesn't change anything except labels. Instead of x, y, z, I use s. Okay, so this is Newtonian second law in Cartesian coordinates. Si are Cartesian coordinates. S1 is x1, S2 is x2, it's y1, etc. Okay. Now, we start from this. Now, in the previous lecture, called Lagrangian in n-dimensional space, I have proved that Newtonian, we are talking about Cartesian coordinates only, that in Cartesian coordinates, Newtonian second law is fully equivalent to equation which is called Euler-Lagrange equation, and it actually looks like this: dl by dsi derivative is equal to dl by dsi. So instead of n these equations, I can use n these equations, where L is kinetic minus potential energy of entire system, which means it's a total of all kinetic energies of all components, and this is potential energy of all components. By the way, I didn't mention it before. I should have done it in the beginning. We are talking only about conservative systems, where potential energy and the force are very much related. That force is equal to minus potential energy by the corresponding coordinate. So this is conservative system. I assume it from the whole lecture. There is nothing. No other systems are considered in this particular case, and that's why we can replace potential with force with potential. Okay. So I have proven in that particular lecture total equivalence of these two things. What does it mean that it's total equivalence? Both of them are Cartesian coordinates, right? Which means that trajectory, which is a set of functions, si of t, which is a solution to these differential equations, are exactly the same as solutions to these differential equations. So these systems of lowercase n differential equations, this one and this one, are equivalent in the sense that their solutions are the same. That has been proven. So in Cartesian coordinates, I can say that, okay, instead of n of these equations, I can put n of these equations. Why? Okay, and here's a very important thing. You see, here we depend on forces and accelerations. They're very much dependent on the coordinates. Now, kinetic energy and potential energy, they are not really related to coordinates in the same way as acceleration. Acceleration means basically you're accelerating along one particular coordinate in this particular case. These are total kinetic and potential energy of the entire system. They are reality, they're physical reality. I mean, if you just think about, okay, I'll change my coordinate system from Cartesian to something else. Well, first of all, these transformations of coordinates, they were also considered in the previous lecture about Lagrangian mass. These are very important transformations of coordinates. So let's say from Cartesian on a plane, we went to polar on a plane. That's a transformation of coordinates. Obviously, acceleration or something, or the force will change. But how about the total kinetic and total potential energy? Well, generally speaking, they are not supposed to be changed with simple transformation of coordinates. What do you mean simple? Well, transformation of coordinates is something like this. If you have coordinates s1, s2, etc., sn, from one hand, these are all functions of t, right? And you have other coordinates. Transformation means that every qi is equal to some kind of a function of s1, etc., sn. That's what it means, transformation. Now, the transformation we really would like to consider in this particular lecture are simple transformation in this particular sense, that qi just functions of s1, sn. Doesn't really depend on time, let's say. I mean, if you have one system standing still and another moving relative to it, obviously there is some kind of a speed involved, and there is speed involved, kinetic energy also should be involved, because kinetic energy is half of mass times speed square, right? So we are not talking about this time-dependent movement of the transformation of coordinates. We are talking about simple one-to-one correspondence. So every point S1, Sn corresponds to one particular point Q1, Qn, and vice versa. And it's supposed to be not time-dependent transformation. So let's call it relatively simple transformation. So for this simple transformation, k and u are supposed to be the same no matter what kind of coordinate system we are using, because these are objective properties. So what's important is this thing is very much coordinate related. This thing is not, because it's just the difference between the kinetic and potential energy, and these are objective physical reality. Coordinate is not objective physical reality. It's our view. It's mathematical representation of position. Energy is not. Energy is physical. It's not related to us. It's related to dynamics of the system which is moving. Okay. And that's actually the way how we will proceed to prove that this is a better approach in some way. Okay, so far in the Cartesian system they are equivalent. Great. So we have this system of equations, and we know that solution to this system of equations in Cartesian coordinates gives a true trajectory in Cartesian coordinates, which means it gives the solution is n functions without index, means it represents everything. So S of t is a solution to this system of differential equations in Cartesian coordinates. Great. Now, from completely different standpoint, let's consider integral from t1 to t2 L of, now function L, kinetic and potential, it depends on kinetic, which is dependent on speed, and potential depends on coordinates of the point. So it actually depends of S of t and S prime of t. Let's call it A. Now, yes, L depends on coordinates and the speed, which are in turn depend on time. That's why the whole thing is actually a function of time. Now, what does it mean, function of time? Well, as the system goes along its trajectory, well, which means every component of the system goes to its own trajectory, but altogether makes a trajectory of the entire system. So as the system moves along trajectory, at any moment in time, it's at certain particular point with a certain particular speed of movement, linear speed of movement, which means its kinetic and potential energies are basically a function of position, where exactly it's located in space, not position from our perspective of coordinates. No, it's a physical position. If this is the system and it goes from here to here, at any point, regardless of our system of coordinates, kinetic and potential energy have certain value. So I will put S here. Why? Because basically the form of Lagrangian depends on the coordinates, the formula basically, which represents, for example, on a plane, if you have Cartesian coordinates, the speed is x prime, y prime, right? So the kinetic energy is 1/2 mass times speed square, which is x prime square plus y prime square. Now, what if you have polar coordinates? Then r and theta are coordinates. What is linear speed? Linear speed is basically radial and tangential. So radial speed is r prime, tangential speed is r theta prime, right? Tangential speed. So sum of square times mass would be a kinetic energy. Formula is completely different, obviously. So if this is S1 and S2 and this is S1 and S2, they look differently, all right? So that's why we will call it with the different letters, basically. And Lagrangian in this particular case, so if this is Lagrangian in system S, where S1 is X and S2 is Y, and this is Lagrangian, which I will call Q. So Q1 is R, and Q2 is theta. We just call it differently because it's more convenient. This is from S1 of T, S2 of T. That's how it's replaced. Well, I put only kinetic energy, but Lagrangian is actually kinetic minus potential. And some formula, and here would be from different coordinates. The formula would look differently. But if at the same time S of t is equal to Q of t, which is actually physical coordinate, I will say equivalent, S of t at any moment of time t points to some point on the trajectory, and if Q is basically a transformation of S, it's supposed to put exactly to the same point, right? Because these are transformation of coordinates, but the point is the same. So expression would be different. In this case it's xy, in this case it's rq, and expression of kinetic energy is also different. But the value should be the same. Again, numerical value of Lagrangian, of kinetic and potential energy, and therefore Lagrangian, must be the same no matter which coordinates we use. That's what's important. So these are supposed to be equal to each other. The value of these. The formula looks differently. Expression of Lagrangian in Cartesian coordinates and expression of Lagrangian in polar coordinates are different. But at the same moment in time, they actually both are characteristics of a moving system at one particular point in space, totally independent of us. That's why the value is the value is the same. Formula is different, the value is the same. So whether I will put S here and S, or I will put Q here and Q here, which means it's a different coordinate system, it will be the same. So what's important is that action is independent of choice of coordinates. I would say rather it's invariant to coordinate transformation if the transformation is simple and nice, like transformation does not depend on time, only on relationship between coordinates. Okay, that's very important. No matter which system I'm using, the value of action functional would be the same for the same moment in time. Okay, now let's go to again physical characteristics. If you have two different points where two different positions of an entire system in whatever n-dimensional space. Now you can have from here to here, to this position, to this trajectory, to this trajectory. Depending on trajectory, we will have obviously different value of action functional. Okay, but let me ask you, which trajectory is actually chosen? All right, that's a very important question. Which trajectory is actually chosen? But let's think about this way. Consider extremals of this guy. When the action functional reaches its extremum, it may be maximum, local maximum, minimum, or saddle point, whatever. Extremum, we know about this. This is all theory of variations which has been covered before. So extremum of functional is achieved when Euler-Lagrange equation actually is satisfied. So exactly this equation gives you a solution which gives extreme value for action functional. So what's really important is that in Cartesian system of coordinates, Cartesian, only Cartesian, this thing is equivalent to Newton's second law, and at the same time, in the same Cartesian system of, I think, extremal, extremal, I don't know how to pronounce extremal of this particular functional, which are totally physical things. Where exactly this functional takes extremum. They are the same. So solution to this in Cartesian coordinates is on one hand equivalent to Newton's mechanics, which means this is a real trajectory we are moving along, and at the same time this same equation gives extremum of the functional. So real trajectory and extremum of the functional must be the same. Well, at least let's put it this way. Real trajectory is a trajectory which both solution to Newtonian second law in Cartesian coordinates and an extremum of action functional. But extremum of action functional should not really depend on trajectory. Why? Because Lagrangian itself, as we have just mentioned, if I will put a different system of coordinates, it will be different expression of Lagrangian, but at the same time it will be exactly the same value. So whether I have LQ of Q and Q or LS of S and S, under this integral it's exactly the same value, and we are integrating this value, which means this is the same value, which means no matter which system of coordinates we will have and express Lagrangian in whatever system, we will still have the same action along each trajectory and the same extremals among all these trajectories. Why is it the same? Well, I mean, let me give you an analogy. If these are 2 points on the plane and you are going this way or this way or this way, and for example, this particular trajectory is the shortest one. Now, What do you mean the shortest? Well, I measure it, and it seems to be shorter, right? So, but you measure it in meters, and it will be the shortest in meters. If you measure it in inches, it will be still the same trajectory, will be the shortest. So extremal of this particular function now, since under integral there is a function which is exactly has the same value for the same t, it will be the same extremum, no matter what kind of system of coordinates you use, in the same way as no matter what unit of measurement we use here, whatever is the minimum will be the minimum. Okay, and that's what's very important. In Cartesian coordinates, solution is to this equation is real trajectory. But solution of this equation is the same in any system of coordinates, which means that in any system of coordinates, my real trajectory where system is moving would be a solution to Euler-Lagrange equation. And that's the final moment which I actually wanted to convey. I don't know how to maybe express it differently, but basically the line of thoughts is the following. From Newton in Cartesian, we go to Euler-Lagrange in Cartesian, which is supposed to be equivalent, we proved that. Now, Euler-Lagrange, at the same time, in the same Cartesian system, is a solution which gives extremum of action functional, but solution to extremum of action functional is a physical property, it's objective property, which is not dependent on our coordinates. And that's why, independently of any coordinate system, if you take an action functional in that particular system, which means you express Lagrangian along the path. So the solution to Euler-Lagrange equation, which delivers the extremals, is actually the one which delivers real trajectories. So extremals of the function of action functionals are trajectories where our object can actually move. Now, which one depends on, if there are more than one extremal, it depends on the conditions, initial conditions, etc., differential equations, obviously. So that's very important. Now, again, I was considering transformation of coordinates which are time independent, as I was saying before. Now, with time dependent coordinate situation is a little bit more complex. I don't want to touch it, but the idea is that Lagrangian is slightly changing if you have a system which is moving. Well, basically it adds something to kinetic energy, but it actually adds a constant. If you have many different ways, and to every way you add the same constant, the trajectory which is minimizing is the same, because everyone is added a certain amount of value, right? So I don't want to go into the details, but again, the problem is the action functional will change, because Lagrangian will change, because kinetic energy, but it will change by the same thing for every trajectory, which means that the trajectories which deliver extremum for action functional, which is solution to Euler-Lagrange equation, would be the same. So, because if you, for example, add some value to Lagrangian, if it's a constant to both sides, it doesn't change anything. So solution would be the same. So that's why I don't want to go to the details, because my purpose was to basically introduce you logic, how you can move from Newtonian second law in the Cartesian system to action functional and its extremization, so to speak, because Euler-Lagrange equation is delivering extreme values for so those trajectories which are solution to Euler-Lagrange equation are trajectories which deliver extremum values for action functional. Okay, what did I miss? I think we are okay. Yeah, we are okay. The only thing is, for example, if you will add to Lagrangian, if you will add something like full full differential of some function, any function, if you will add it here, since it's a full differential, the solution, if you will have plus df of st for dt, so it will be sum of two integrals, and the second integral will be integral from t1 to t2, or from df by dt and dt. So it will be basically formula Newton-Leibniz f2 minus f of t1, which is constant. It doesn't really depend on anything. So adding this function would just add action, would add some value, this value, to action functional, which again does not change which trajectory is extremum, because again, like in my comparison with the way from point to point, if you add a constant to all points, the one which was minimizing before will be the same minimizing after. So that's basically it. Now, I do suggest you very strongly to read notes for this lecture. So you go to unizor.com, you choose Physics Plus for all, you choose, well, basically the whole topic Lagrangian is important. Now, this particular lecture is called Principles of Lagrangian Mechanics, but it's very important because it's very important to take the whole actually piece devoted to Lagrangians, because I actually related to this. First of all, theory of variations is very important, because that's how you introduce the Euler-Lagrange equation. You cannot really do this before you know everything about theory of variation, at least in the framework of my course. You also have to be able to know why Lagrangian is equivalent to Newtonian second law in Cartesian system, which has been proven in a lecture about Lagrangian in n dimensions. So the whole thing should be definitely studied, and listen to lectures or read the material. And on this particular lecture, there is also notes for this particular lecture, and the notes are very detailed. It's really like a good textbook, very solid textbook. So I do suggest you to read the notes for the purpose of understanding this concept, the transformation from Newtonian second law to Lagrangian mechanic in generalized coordinates. That's it. Thank you very much, and good luck.